Welcome to video number 5 of this presentation called What Goes Inside an iPhone. The study of the iPhone was divided into 5 blocks called Energy and Mainboard, Access, Radios and Antennas, which is today's subject, Movement and Location, and finally Cameras. There is also an important introductory video. Let me show you all the videos together. Here they are. If you haven't watched the videos number 1, 2, 3, or 4, I suggest that you do before you proceed. As mentioned, today's subject is radios and antennas. I'd like to start by showing the big picture and by addressing two difficult questions. How many radios are there in a modern smartphone, and how many antennas? The big picture is this one. You probably guessed from the previous slide. There is a cellular radio, which is currently in the 4th generation. And this is the radio that communicates with the cell towers. There is the Wi-Fi radio that communicates with the nearby router. Bluetooth radio that communicates with nearby device, printers, for example. The near-field communication radio, which is for making payments. And finally, the GPS radio, which communicates with satellites. So let's try to find the number of radios. For cellular communication, there is support for 4G, but also for older generations. This is the case of iPhone 11. But because only one can be on at a time, some sharing can be done in the RF part. For Wi-Fi, there are 2 radios on at the same time, 2.4 and 5 gigahertz. Bluetooth single radio, 2.4 gigahertz, NFC single radio, 13 megahertz, and GPS, you have a mandatory signal and an optional signal, 1.6 and 1.2 gigahertz. We'll see details later. So no matter how you count the number of radios, for example, it could be the number of transceivers, what you get is something a little above 5. About the number of antennas. For cellular, there is a main antenna. There might be a diversity antenna. There is MIMO. The total is typically between 2 and 4 antennas. For Wi-Fi, there is MIMO, typically between 2 and 4 antennas. For Bluetooth, single radio, single antenna, but this might be shared with the Wi-Fi antenna. For NFC, single radio, single antenna. And for GPS, we can assume a single antenna. So the total typically lies in this range here, 6 to 9. An additional question is, which radios are bidirectional? In other words, which radios send and receive information? The answer is all but GPS. We receive data from satellites, but we do not send anything back to them. Okay, the cellular radio. It communicates with the cell towers, currently in its 4th generation. The standard is called LTE, long-term evolution. Let me show you all the generations together. Here they are, more or less 10 years apart. We are now in 2020, and 5G has just started. The 1st generation was analog, all the others are digital. And after this point here, we had voice plus data. The main difference between one generation and the previous one is the speed of data. For 4G, we have 100 megabits per second downlink and 50 megabits per second uplink. LTE Advanced and LTE Advanced Pro are already available in some places with speeds of 1 and 3 gigabits per second. The practical numbers, however, fall short from these theoretical limits here. These are the standards supported by the iPhone 11, and here are the official frequency ranges. Looking at their specifications, you see that not all bands are supported, so the ranges are a little shorter than the maximum, theoretical maximum here. But you see also that there is an LTE Advanced option here. A major concern in the design of a radio is the size of its antenna, and a smartphone is small. which makes it even more difficult. So I want to make a few comments about that. The typical or reference size of an antenna is lambda over 4, where lambda is the wavelength of the signal to be transmitted or received by the antenna. And it is given by this equation, speed of light divided by the frequency. For example, for a frequency of 2.4 gigahertz, could be Bluetooth, for example, the antenna length would be 3.1 centimeters. This number tells us that this antenna can fit well inside a smartphone. But we have to remember that there are other frequencies much smaller than this one, and there are more than 5 antennas, which should not interfere with each other too much. So their positions cannot be done randomly. Here's the full table with the full ranges supported by the iPhone 11. So this would be the range of size for the cell antenna, for the Wi-Fi antenna, and so on. So if you look at all this, except for this part here, let's say taking the middle here, you see that they are a few centimeters, which are okay. There is one, however, which is 5.45 meters, which of course does not fit inside the smartphone. So we'll see later how the problem is solved in this case. Some implementation approach to save space for the antennas. The IFA, which is inverted F antenna, the PIFA is planar FA, slot antenna, etc. Here's an example of IFA. This is the inverted F. Is the radiator. 2 other examples with 3 radiators, 1, 2, 3, and the same thing here, 1, 2, 3. Let me show you the antenna in the iPhone 10. Here it is. It is installed down here. It's just lifted here, lifted so you can see it better. So this is the main cellular antenna. Other antennas will be seen as we move to the next topics. It is important to make also some comments about signal levels. Just as a reminder, the power in communication is measured in dBm, which is the power with respect to 1 milliwatt in a log scale. So if the power is 1 milliwatt, for example, this ratio is 1, log is 0, and this gives this very important reference here. Every 10 dB that you go up here, you multiply by 10 on the other side. Every 10 dB that you come down here, you divide by 10 on the other side. So remember, minus 30 is 1 microwatt. So level of the signal received from the cell tower. There is no official definition for this range here, but around 90 is accepted as a dividing line between good signal and where the signal starts becoming too weak. So this minus 30 is 1 microwatt, minus 60 would be then 1 nanowatt, and minus 90 is 1 picowatt, 1 picowatt. Let's look at the Wi-Fi signal. Again, there is no official definition for this range, but minus 50 is more or less accepted as a good dividing line. So if we take these 2 conditions as equivalent, minus 90 for LT, minus 50 for Wi-Fi, this means a 40 dB difference. And this means that the signal from the Wi-Fi router has to be 10,000 times stronger than this one for an equivalent situation. Let me show you an actual measurement. So this is for LTE, minus 109, and this is for Wi-Fi, minus 54. So minus 109 is somewhere here, and minus 54 is down here. It's incredible that with just minus 109 dBm, the device still works. It's not great, but it's still operational. So that's quite impressive. Now about the level of the signal transmitted by the cell phone. It depends on the distance to the tower. It has to be relatively strong because the signal attenuates with the square of the distance. And typically, it falls in this range here between 0 and 30 dBm, meaning 1 milliwatt up to 1 watt. If you are close to towers, then the signal is close to 0 dBm. If you get away from towers, for example, if you are traveling, it grows a little bit here. Of course, if communication when you are away from towers causes your battery to last less. The next topic in the cellular radio is MIMO, multiple input, multiple output radio. It's a major feature to increase data rate, makes use of multiple antennas as illustrated here. There are two types, single user and multi-user, though single user is virtually gone. The most common implementations are 2x2, meaning 2 transmitters and 2 receivers, and 4x4, both available in LTE Advanced and LTE Advanced Pro. The case of iPhone. In 2017, it was 2x2 for all devices. In 2018 and 19, it is 2x2 for the regular device and 4x4 for the top devices. Note that in all cases, it is multi-user. Additional details on MIMO will be given in part 12, which deals with the Wi-Fi radio. An interesting test is presented next, illustrating the power of MIMO. It shows the download speed of an iPhone X against iPhone XS Max. Note that 10 is 2x2 MIMO, XS Max is 4x4. So you expect the speed of this one to be up to twice as big as the speed of this one here. And here are the results. They're published at this website. In gray is the iPhone XS Max, in yellow the iPhone X. So taking this as a reference, this 400 megabits per second and this 200, so it's as expected. We close the part on cellular radio by showing the location of some of the RF components in the logic board. First, for the iPhone X, here's the LTE transceiver, the Wi-Fi plus Bluetooth module, and the LTE modem. Now for iPhone 11 Pro, the Wi-Fi plus Bluetooth module combined again, the LTE modem, and the LTE transceiver. Okay, we turn now to the Wi-Fi radio, which is the radio that connects the router to the smartphone. In our case, both sides can have multiple antennas, as we'll see in a second. In the case of the iPhone 11, the Wi-Fi version is version 6, which, by the way, is one of the most complex radios ever proposed. Here is a summary of the Wi-Fi versions from version 1 to 6. This was 20 years previous to the current version, which was published last year. And I want to comment about this maximum link rates here. This is the very maximum that you can get under very, very favorable conditions. And this is not a minimum, but another maximum, just under other conditions. So let me see an example here. For example, in the case of Wi-Fi 5, this one here. The left bound is for one user, one smartphone, for example, one antenna, and an 8 megahertz channel. So the maximum rate can be 433 megabits per second, so maximum rate. And the right bound is for 8 antennas, 8 streams, a channel that's twice as large, and perfect signal-to-noise conditions. So you get this maximum rate of near 7 gigabits per second. So both are maximum values under different conditions. The signal-to-noise ratio not only affects the formation of channels, like here, putting two of these together to form this one, but also the choice of QAM modulation. To use the most dense modulation, you need very, very good signal-to-noise ratio. If the noise grows, the system will automatically switch to a simpler or less dense modulation. An interesting number is obtained when we divide the maximum link rate by the channel length. For Wi-Fi 6, it is 9608 from up here by 160, and this gives 60 bits per second per hertz. It means that for each hertz of spectrum, we are downloading, in this case, 60 bits. Just for comparison, this number is already 40% better than the previous Wi-Fi version. And looking against the very first version, we have 11 megabits per second from up here. And the channel length was 22 megahertz. So the result was 0.5 bits per second per hertz. Even though this 60 bits per second per hertz can only be obtained in very, very favorable conditions, it gives a good idea on how well the spectrum is being used. A few other features that are also very important. One is OFDMA, which allows channels to be shared by several clients. And these are very complex feature to be implemented in the future in Wave, what's called Wave 2. Another important new feature, as I mentioned already, is 1024 points QAM modulation. So you have 10 bits per point or per symbol. So the old one had only 16, then this whole square became one quadrant here, the whole square one quadrant here, the whole square one quadrant here. So you see the points are very, very close, and then you need a very low noise for this to be usable. And also now you have 8 streams in the multi-user MIMO with extended functionalities. In the previous one you had also 8, but it was never implemented above 4. And you have beamforming for directional communication, so you direct your power towards the user, so that improves communication, obviously. And both of OFDMA and multi-user MIMOs are for downlink now and uplink in the future, so for the Wave 2. We look now at the Wi-Fi channels, starting with the 2.4 gigahertz band. There are 14 channels of width 22 megahertz. Here they are, 1 to 14. The last 3 are not used in US and some other countries. And the maximum number of non-overlapping channels is 3. So you can see this in this figure. Besides, if the last 3 are not used, then the only option, if you want to use the maximum number possible of channels, which is 3, is the combination 1611, which is here, 1611. And that's the reason why this combination is so popular and so crowded. In the case of 5 gigahertz, there is more space, so it's more organized. There are 25 channels. The width is 20 megahertz, and there is no overlap. So you can see all 25 channels here, and they can be put together to form channels of 40, 80, and 160 megahertz. In this other figure, we show the channel numbers. So these are the channel widths, and these are the channel numbers, official numbers. The initial channels, let's look down here, up to 48 or 64, so up to 48 in some countries, so you take this slice here, or up to 64, you take this block here, are reserved for indoors. So you have more spectrum for your routers in the 5 gigahertz band, which unfortunately has a lower range in terms of distance. About MIMO, recall that it means multiple input, multiple output radio. And there are 2 options, single user and multi-user. Current Wi-Fi routers and smartphones use only the multi-user option. Most routers have 3 or 4 antennas. Most smartphones have 1 or 2 antennas. I'm talking about Wi-Fi antennas here. In the case of the iPhone, is here. So Wi-Fi versions 5, 5, and 6, and MIMO type multi-user in all of them, and MIMO 2x2 in all of them. And this version 6 was released in 2019, so it makes sense that it only showed up in the iPhone 11. Just to understand the differences, a single user MIMO has multiple antennas at both ends. Only one user at a time with multiple streams, relies on multiple propagation paths. Knowing the phase of its antennas, the receiver can separate the data stream. It's in very intense signal processing required. This is an illustration on how it works. So this is a 2x2 system. So the router here communicates with one user. So you have 2 antennas there, 2 antennas here. Then it stops, communicates with the other user, stops, comes back here, and so on. It was this approach was not implemented in smartphones. Now, multi-user MIMO. The router and client can have up to 8 antennas. Those smartphones are more likely to stay between 2 and 4. Beamforming is used. The phased antenna array detects the direction of the clients. This is called channel sounding, after which multiple directional beams are formed, so the transmission power is used more efficiently. And this is for the downlink and uplink, though the uplink is planned for the future, in the Wave 2. This is an illustration of the operation of multi-user MIMO. In this first figure, there are 2 clients, both are off, so the router has no preferred direction of transmission. Next, both are turned on. So after channel sounding, the router establishes directional beams. You can see here. Now it goes beyond the user, certainly providing a stronger signal than it had here. And in the third figure, one of them is turned off. So both beams are directed towards a single user here. This is what is being implemented in recent iPhones. Some examples illustrating the differences between single-user and multi-user MIMO are shown next. Example 1. The single-user environment contains a 3-antenna router and 3 smartphones with 2 antennas each. So each one is served during 1/3 of the time with 2 streams. The total is 2, and so the usage factor is 2 out of 3, or 2/3. In the multi-user case, there is a similar router and 3 smartphones, but with a single antenna. So each one is served with 1 stream during the whole time. The total is 3, and the usage factor is 3 out of 3, or 100%. Conclusions: multi-user wins with just 1 antenna, which is less cost and less power consumption, and there is no MIMO gap in the multi-user case. Example 2. One of the users has left the environment. So here each user is served during one half of the time with 2 streams. The total is still 2. The total here now is 2. So conclusions, it is a tie, but the multi-user has just 1 antenna, so indeed it wins. And there is MIMO gap in both cases. Final example. Now this is the same, but there is a replacement of 1 smartphone with a single antenna with a dual antenna. So the factors are now 2 and 3. Conclusions are that multi-user wins with fewer antennas on average, and there is no MIMO gap in the multi-user case. To conclude Wi-Fi, I would like to address 2 questions. First, in few words, what are the differences between 2.4 gigahertz and 5 gigahertz Wi-Fi from a user perspective? A short answer could be the following. For 2.4 gigahertz, on the positive side, longer range indoors and outdoors, can cross obstacles like walls more easily. On the negative side, lower speed, crowded spectrum more subject to interference. For 5 gigahertz, positive side, higher speed, larger, cleaner, mostly free spectrum. On the negative side, shorter range indoors and outdoors, and more difficult to cross solid objects. The second question is, Wi-Fi router speeds look great, but what is the speed of my device? This is a difficult question. What I did here, I wrote down the numbers from the Wi-Fi 5 documentation for 1 stream and the top 3 modulation options. For 2 streams, all we have to do is to multiply everything by 2. And for the 2.4 gigahertz, my guess is that I would be able to go beyond the basic channel, and I would be able to get the most dense modulation. For the 5 gigahertz option, because it's a clean spectrum, larger spectrum, I'm assuming that I would be able to get the most dense modulation and a combination of 2 channels, or even a combination of 4 channels. So the result, the maximum would be somewhere inside here. For the Wi-Fi 6 case, I went to the other documentation. I did the same search for numbers, and same reasoning. I got these results here. Let's compare these estimates to a test published recently. Here it is for 2.4 and 5 gigahertz. It can be seen at this address. The big surprise was that the speed is about the same, even though the 10S Max is Wi-Fi 5 and the iPhone 11 uses Wi-Fi 6. I don't know the conditions under which this test was developed. Too much noise is not likely because that doesn't happen in the 5 gigahertz range. Maybe the data source was limited, or maybe I'm missing something. So anyway, let's compare these numbers to our estimates. We can take this 80 megabits per second as a reference as we approach the router, and we can take the 500 megabits per second here. So 80 and 500 megabits per second. Okay, so Wi-Fi 5, 2 streams, 80 and 500. So 80 is close enough, 500 is well inside, so that's a good fit. Of course, if it fits here and the data is about the same, it will not fit well in the other case here. We close the part on Wi-Fi radio by showing some Wi-Fi antennas. First, for the iPhone 10, here is the module that we saw before for Wi-Fi plus Bluetooth, and here are the antennas, very small. Next is for iPhone 11 Pro. Here's the module, again for Wi-Fi plus Bluetooth, and here are the antennas. The next radio in our list is the Bluetooth radio. Its purpose is short distance communication between mobile and or fixed devices. There are many applications for it, like wireless headsets, wireless alarm systems, computer printer linking, energy metering, Internet of Things, etc. Apple informs that iPhone 11 is equipped with Bluetooth 5.0, which is the newest version. This version was published in 2016. Some of its features are listed next. The frequency is around 2.4 gigahertz. It's a very low energy device, trading data rate for range. A little battery can last several years. The low energy data rates are 2, 1.5, and 0.125 megabits per second. The 2 megabits per second being the most popular, but if you can save even more battery, you can go down here. Version 5.0 has been in the iPhone since iPhone 8, which makes sense because the iPhone 8 was released in 2017, and this version of Bluetooth was published in 2016. There is a high-speed option in the old version 3 of Bluetooth for 54 megabits per second. A common question about Bluetooth regards its range. How far can the signal go? The Bluetooth Special Interest Group has an estimator, which is available at this website. And I ran it for the 2 megabits per second option with the gains of the transmission and reception antennas set to 0 dB. I also chose 3 powers, 0, 10, and 20 dB. Remember that these are 1 milliwatt, 10 milliwatts, and 100 milliwatts. And here's what I got. 2 important conclusions can be drawn from here. Looking at the indoor case, which is by far the most common, we can take the minimum and maximum and say, well, maybe the maximum is between 13 and 30 meters typically, So this is a good range to remember. The other conclusion regards the power. It doesn't help much when you are working indoors to crank up the power. For example, here you go from 1 milliwatt to 100 milliwatts. You are multiplying the power by 100, but the range does not get multiplied even by 2. So that's another good conclusion to remember. We turn now to the NFC radio. Here is a typical situation. Its purpose is to make short-distance contactless payments using a mobile device. And the designation near-field communication is due to the fact that the involved distances here, which are below 20 centimeters, are much smaller than the wavelength of the transmitted signal, which is 22 meters. The iPhone 11 comes with NFC radio and it has support for reader mode. So let me show you a few features of this kind of radio. It's for point-to-point communication. The maximum distance for security is 20 centimeters, though in practice it is usually below 10 centimeters. The radio frequency we saw before, it's 13.56 megahertz, so a huge lambda of 22 meters. And low frequency means huge antenna, but since the distance is small, a simple coil suffices. The data rate can be 1, 2, or 400 kilobits per second in round numbers. And reader mode, which is mentioned here, means that the device can read NFC tags. To close this part, let me show some implementation examples. This one is from TDK. It's a very, very common implementation. It combines the battery charging coil with the NFC coil. So you see many turns here, a few turns there. Another option is to have the NFC antenna at the top of the cell phone. Our final radio is the GPS radio. And we start with this beautiful artistic view from Wikipedia. Okay, it says here that the iPhone 11 supports GPS, but it also mentions GNSS. So let's see what this means. GNSS is any satellite navigation system with global coverage. There are 4 of such systems in the world. Here they are. GPS from the USA, another from Russia, one from the European Union, and finally one from China. All 4 are supported by the iPhone, and these 2 are still being completed. And there are also 2 regional systems from Japan and India, which have the advantage of being more accurate. GPS, which stands for Global Positioning System, started in 1978 and is open and free since 1994. Being it by far the most popular, it is to that system that this presentation is related. The GPS system. Originally with 24 satellites, today with 31, plus 2 in test and 9 in reserve. Their orbit is at 20.2 thousand kilometers. Just for comparison, the geostationary satellites which are used for communication are at 36,000 kilometers. So these go around the Earth to, exactly in 24 hours, while this takes exactly 12 hours. The satellites are equipped with atomic clock for synchronization. And in open space, at least 8 or 9 satellites are visible anywhere on Earth. About GPS communication. The fundamental GPS codes are called CA for course acquisition and PY for P for precision, Y after the code is encrypted. GPS satellites transmit 1 or 2 frequencies called L1 near 1.6 gigahertz and L2 near 1.2 gigahertz. L1 is always used and carries both codes mentioned above, while L2 is not mandatory and carries only the PY code. Communication is unidirectional, as I had already mentioned, satellite to device only. Advantages of dual frequency GPS: redundancy of POI, lower chance of jamming, and more importantly, if L1 and L2 are transmitted, the ionospheric delay error can be cancelled out. This error, by the way, is the main error in the GPS system. It can be minimized with the use of two frequencies, as I just mentioned, or with the help of fixed stations, because then their location is known precisely and can be compared to the received information from the satellites, and the difference can be used for corrections. This is used in augmented GPS, discussed in a few seconds. If only L1 is used, an ionospheric model is employed. So this is an approximation. About the receiver, which in our case is a smartphone. It must see at least 4 satellites for full GPS operation. It solves a system of equations to determine the latitude, longitude, and altitude. If more than 4 satellites are visible, the precision increases. The typical precision, by the way, is between 30 centimeters and 5 meters. It depends on whether 1 or 2 frequencies are received, on the quality of the signal, and more importantly, on the number of satellites that are visible at that particular location. Here is an interesting illustration from Wikipedia. It shows the satellites that are visible from a fixed point on Earth. You see the number here. It's never below 6 for the original 24 satellite system. And that location is the city of Golden in the state of Colorado, shown here. To conclude, a few words about assisted or augmented GPS. It is illustrated in this figure, which has 2 parts. The upper part is the GPS system. Here are the satellites. Transmission always down, nothing goes up. And in the lower part, there is a stationary GPS receiver. So its location is well known, so the AGPS server can compare it to the location information received from GPS, and the error will help the server produce the ionospheric delay map, which can be sent to the user, in this case a smartphone, improving the accuracy of its location. Another way of helping is in the so-called time to first fix, TTFF, which is the time it takes for the user to synchronize with the satellites when it's turned on, for example, which can take several minutes, but with this information present, it might be reduced to just a few seconds. In summary, this is the navigation system. This is not a replacement, but it is an important helping tool which is becoming more and more popular. And with this, we conclude video number 5. I thank you for watching, and I invite you to join me again for video number 6.